Oh, hi. Welcome, everybody. Hope everybody is not having to struggle too hard through this January winter we're having. So we're going to switch up the way we do things today. So we're first going to have the guest lecture, and then we'll have, the little thing that I do later on after that. So be sure to stick around. So I want to introduce Steve Collins. He's new here at Stanford in mechanical engineering. He arrived, before he came here, he was at Carnegie Mellon, where he directed the experimental biomechanics laboratory and taught courses on robotics and design. He received his BS from Cornell in 2002 and his PhD from University of Michigan, go Blue, in 2008, and performed postdoctoral research at Delft. He has published in a lot of journals. He's a member of the scientific board of Dynamic Walking Conference in 2013, the recipient of the American Society of Biomechanics postdoctoral young investigator, again in 2013, and he had the best paper in ICRA conference, best medical robotics paper, and recently was voted to the CMU Department of Biomedical Engineering Professor of the Year. So we'll see how well he does here at Stanford. So let's welcome Steve to Stanford.
Introduction. Very kind. Oh, I hear someone else I know. All right, you guys can hear me? All right, great. So thanks. Yeah, I'm Steve Collins, very new here to Stanford, and I'll talk today about some of our work in exoskeletons and prosthetic limb design. Please feel free to jump in at any time. I will probably kind of go quickly and have lots of things to say, but this is more interesting if it's a dialogue, so jump in, interrupt me as you please. Hi. Sorry, this is my son Max, and I guess his mom is there somewhere. Hi guys. Off to a roaring start. Okay. So today I wanted to talk about three things with you. The first is a really challenging design problem that we're working on in my lab. The second are some tools we're developing that give us traction. And the third are technologies for translating effective designs into mobile devices. So first, our challenge. What we want to do is design prosthetic limbs and exoskeletons that improve human mobility, especially in terms of outcomes like energy cost, or speed, or balance, and especially for people with disabilities, like amputation, or stroke, or simply from the effects of aging, or enhanced performance for people who have to walk and run under very arduous conditions, like these relief workers. And this has been a problem that's caught popular interest for a long time. We've had a lot of very smart people work on this, well-funded groups, big groups, companies, and yet nearly everything we've tried has failed to deliver a benefit to the user. And the handful of devices that have succeeded have delivered relatively modest benefits compared to what we think should be possible based on simulations. And the question is why? I argue that the problem is that we don't actually know what these devices should do to assist their user. Humans in our bodies and our brains were very complicated, and each one of us is unique, and we're all constantly changing. And that severely limits our ability to predict how a person will respond to a new device based on our intuition or simple mathematical models. And oh, okay, yeah, cool. Sounds good. That's, we've been basing our design process on a guess as to what the device should do in order to help the user. And going quickly to the design of the robotic systems. Sometimes I refer to this as the Tony Stark problem, right? popular culture would have you believe that all you need is a little bit of money, a knack for fixing up old cars, and super suit, you know? And the truth is it's much harder than that. So if our predictive tools aren't effective for this design problem, then what we find ourselves in is an iterative process, an evolutionary process. And then what we should do is develop tools that speed and systematize our search. And in my lab, we've been developing 2 sets of tools towards that end. First are versatile hardware systems that we call universal device emulators, which are intended to allow you to get to experimental tests of new device designs on people faster. And the second are algorithms for what we call human-in-the-loop optimization, which are intended to allow us to navigate the vast space of potential assistance strategies faster. So this is a typical emulator system in our lab. There's a lightweight, instrumented end effector that the person wears on their body, and it's tethered to powerful off-board motors and computers. And the way we use these is kind of like virtual reality for your leg. So the emulator can render to the person a wide range of device designs without the need to actually build these specialized devices. And that way you can get to experiments on people in a matter of days or even minutes rather than years, as you would have to if you were designing each device separately. So this makes the process much faster. Once you've developed that off-board motor and control hardware, making new end effectors that you wear on your leg gets relatively easy. For example, this is a 2-degree freedom ankle-foot prosthesis intended to explore new ways of improving energy economy and balance for people with transtibial amputation. And by many measures, these systems are the highest performing prosthetic limbs and exoskeletons in the world in terms of, say, peak power or torque or closed-loop torque bandwidth. So how well they can render those virtual devices to the user, because we're leveraging the laboratory setting. Now, there are some things that we can't do because you're stuck tethered to that big chunk of metal behind you. We can't go out into the world. There are some environmental disturbances that we can't really emulate well in the laboratory. But within the laboratory setting, you get this unparalleled versatility in your system. And in particular, they open up new kinds of design approaches, such as human-in-the-loop optimization. So as I mentioned earlier, it's really difficult to predict how a person is going to respond to a new device, not only because we're very complicated, but because individual differences between us can lead to opposite responses to the same system, which we've seen in our experiments. And this is especially true in patient groups where you have a lot of versatility, or actually variability, or heterogeneity as a result of the injury. And people also, their response to a device changes strongly over time, especially when you're learning to use a new system. So what we really want are ways of automatically discovering new assistance strategies and individualizing them and continually adapting them to a person's needs. One way to do that is to measure human performance while a person is interacting with an assistive device. Feed that information back to an optimizer that then systematically varies device behavior so as to maximize human performance. Note that in this system, we are measuring the thing we really care about, not some intermediate device outcome or some guess as to something that will correlate with an outcome we care about. Now this may seem obvious, right? When you say it like this, we're going to maximize human performance by measuring human performance and then trying to maximize it. Yes, obviously, right. But almost all work done in this domain operates entirely on this side of the diagram, where given some desired change in human capability or behavior, the designer assumes that they know what the device should do. Almost no one is close to them. Now, this is not to say that this isn't also a hard problem. The measures of human performance we might use, like measures of metabolic energy consumption, which is the biochemical energy used by your body to do things like move around, or balance. These are noisy measurements. They take a long time to get a single value. And there's substantial time dependence. There's hysteresis. And so these features make it a challenging optimization problem. It's also really expensive to get each evaluation. And you can only evaluate a few control laws before the person becomes tired. So a lot of the methods the very well-established methods that work well in computer simulations don't work well for optimizing device function for assistive devices. This is a problem we've been working on for about 5 years, and we recently had a breakthrough. We found a way of discovering the exoskeleton assistance patterns that minimize energy consumption while walking. And here's how it works. So the person wears an exoskeleton on their legs and begins walking. The exoskeleton applies some pattern of assistance defined by, we call this a control law. So in this case, we're looking at the torque provided by the device that's sort of pushing your toes down as a function of time, normalized to the time that it takes to make one step. And a series of control laws are applied, each one for a couple of minutes. And during that time, we measure your metabolic rate using indirect respirometry. So we measure the concentration of oxygen and carbon dioxide that your body absorbs and produces respectively. And we can use that to estimate the biochemical energy consumption inside your body, mostly in your muscles. And with a couple minutes data, we can estimate what your steady state metabolic rate will be. We do that for each control law that we're considering, which forms a generation of device parameters. And then using an evolutionary strategy, we use a covariance matrix adaptation evolution strategy. You guys all know this, right? CMAES. It's old hat. Anyways, it's just a genetic algorithm. Given some data for a set of potential designs, it tells us a new set of potential designs that are worth exploring. And after we go through this loop a few times, we have a pretty good guess as to what the best device characteristics will be for a given person. So when we performed this optimization, we looked at assistance in terms of torque applied at the ankle joint. For the who's interested in optimization in the audience? 2 people. Okay. I won't go too deep into this, but there were 4 parameters that we tuned. They set, for example, how high the torque was, when we hit that peak, when does the torque start, and when does the torque stop. And with just those 4 parameters, you can get lots of different patterns of assistance. Some of them we expect to be really helpful, and some we expect to make walking harder. We applied those patterns of assistance to an exoskeleton worn on one ankle during walking with one of our emulator systems. And we tested 11 participants without disability for this study, as we're just still establishing these techniques before we get into patient groups. And people walked on the treadmill at a typical speed, and we tried to optimize metabolic rate. Our main finding is that optimized assistance reduced energy cost by 24% on average. And it reduced energy costs for everyone in our study, with improvements ranging from 14% to 38%. And these are really big improvements in energy economy. This is about 4 times the best improvement that we had found by hand tuning the same device. It's about 3 times better than our lab's best improvement in energy economy with any of our devices. And it's a better improvement in energy economy than any other exoskeleton to date, including devices operating at both hips and knees and ankles. So this optimization process seems to be working. We're discovering assistance strategies that produce far better results than we could by hand tuning. If we look at the optimized patterns of assistance, shown here, each color corresponds to a different participant, you can see that they're really different. This is particularly visible in the timing of onset, which ranges from it covers about half of the possible range for that parameter. And so that emphasizes the importance of customization and the effectiveness of the technique. And when we analyze these torque patterns, we can also compare them to some prevailing ideas in the design of these devices. So often people will say, we know what to do, we just measure what the biological ankle normally does, and then we'll play that back with our device, and that will maximize benefit. That turns out not to be true, right? The biological ankle produces a lot more torque, and it starts right at heel strike. So that's not optimal. Another common idea in the field is if you want to drive down the person's energy consumption, just drive up energy input from the device, right? First law of thermodynamics, simple. However, these trajectories do not comport to that idea either. You could get a lot more energy input by having the torque start later and having higher torque and having it end later. So as we expected, based on our experience wrestling with these design challenges, it's not as simple as you might think. Another sort of unexpected finding of the study was about the importance of learning on the human side of the system. So this takes a little unpacking, but in addition to these optimized patterns of assistance, we also tested everyone on a fixed static pattern of assistance that was the best we discovered in a previous study. And when we look at their energy cost in the condition where the exoskeleton did nothing, and compare it to when the exoskeleton applied that static, consistent pattern of assistance, in this study, the optimization study, and in our previous study, something funny jumps out. So in this study, the static assistance pattern produced a 19% improvement in energy cost, which is very big. In our previous study, it had only improved energy economy by 6%. Same pattern. So what's different? Well, the main difference between this experiment and the previous experiment is the condition under which people adapted to the device. So during that optimization phase, remember, they're experiencing all these different control laws. And in retrospect, some of those control laws were really tough to work with. So they forced people to change their motor control patterns and try different things. And it seems like this helped people to learn how to use the device. And in other related disciplines, we've seen sometimes that this sort of forced exploration is necessary in order to learn how to become expert in some new biomechanical skill. So we think that's part of the secret of success. And you can kind of see this in a video of one of our participants. Here, the subject has no exoskeletons on. Then he wears them with zero torque mode, where they're not doing anything. Here's the beginning of the optimization process. You can see the gait is highly variable. Looks like it's difficult. This is after convergence. Right. So we're now convinced that, when we first started this problem, we thought that our main challenge was discovering what the device needed to do to assist the person. And it's increasingly clear that it's equally important that we help the person learn how to best use the device. That is, the person learning to use the device is equally important as the device learning what the person needs. So an effective algorithm needs to address both of those challenges at the same time. We performed a few follow-up studies to see if this approach applied to different circumstances. So our first study was with one ankle. We also tried it with 2 ankle exoskeletons. And we optimized during normal walking, fast walking, uphill walking, loaded walking, running. In all cases, we found a big improvement in energy cost compared to zero torque or not wearing an exoskeleton. We tried it with slow walking, and the exoskeleton drove its torque to 0. So it seems to work even when the best thing for the device to do is nothing at all. We also tried optimizing muscle activity rather than metabolic rate, and it was effective there. So it seems like there are a lot of circumstances where this kind of approach can work. So taken all together, we think that this is evidence that emulators and human-in-loop optimization are really strong tools for improving the design of exoskeletons and prosthetic limbs. And I think as the field moves forward, we're going to see these become really essential to the upcoming success of these devices. And what we're working on right now at Stanford with some new collaborators like Emma Brunskill in computer science is improving our algorithms to get faster learning in the person and faster optimization. For instance, by breaking those procedures up and treating them differently. Okay, I'd like to pause now and solicit your questions yes?
Yes,
Yeah, please.
I have a few questions. So first of all, does your optimization method affect the hardware or the software or both?
It's all in software so that you don't have to change the hardware. But these systems are designed to be, so here you've got, the participant wears the device, and then back here you can see these huge motors. Like, these are 7 kilowatt AC servo motors. They weigh, 15 kilograms each. So these are huge, very, very powerful systems. So they contain kind of all variations on this type of exoskeleton. So in that sense, they're imitating different kinds of hardware. Our purpose is to avoid changing the hardware. Now we have done things like, it's hard to emulate mass changes, right? And the weight of a device, right, might make a big difference to a user. So we've done things where we connected little tubes that are with air pressure and little steel ball bearings in them. So you can quickly shoot a few kilograms of mass into the person's device and then shoot it back out to change the mass, which is really fun. Does that answer your question?
It's just the first.
The first, yes, okay, yeah.
So, would this work on any existing exoskeleton and companies working with you or want to work with you, or what's their feeling about it?
Yeah, that's a good question. Do we have anyone in the audience who works in an organization that develops exoskeletons? Yeah, I think there's some interest. Yes, the techniques can be applied to any system. Right now the way we've been trying to use this is in a very early stage design process so that the physical plant that you get is capable of doing the things you need it to do. So you know what the commercial device that goes out into the field should look like. It's certainly, this class of algorithms should apply to any device. And the long-term vision, of course, is that you maybe go and buy some exoskeleton at the shoe store, and you put it on, and then you push the training mode, and you go jog or you walk around, and it slowly learns you, you slowly learn it, and over the course of a day or two, that optimization occurs, and then it gives you big performance enhancements thereafter.
So I would imagine the optimization is like individual per person. Everybody's going to be different.
Yes.
And I would also imagine that it might change as the person adapts to the exoskeleton. Is that correct? Or have you gone that far to know that?
No, we have not done a longitudinal study yet, and that's something that we're quite interested in. Yeah. Anybody else? Yeah.
I think it's a little bit related to the second one. So Tesla, when you're driving around a Tesla, Tesla is constantly recording and collecting data, and one day Tesla's going to run a command line to DreamIs, and then your car will be able to drive itself. You know, the idea is to be collecting from tens of thousands of drivers.
Yes.
Can you measure the way people walk and then take that data and overlay it with the data you have from your device and say, this is how it would perform walking down that hill if you had it on?
Yes, that's an excellent idea, and in the long term, we'd like to do that. Now, first we need to get, a few tens of thousands
Right.
of these things out into the world.
It's on, it records how you step.
Well, so the Tesla provides a benefit already, right?
Yeah.
You have a car, it takes you somewhere, you look pretty sweet while doing it. But most of these devices to date have been expensive exercise machines, right? So first we need to be able to demonstrate that something is worth having. And then there's then you have the economic situation where you can actually make them and sell them and get some out into the world and start to collect the type of data that you need. Humans are, so complicated, and I'm not sure exactly what signals we're going to need from people to be able to map from the way you behave to what your device needs to do to assist you. It may be encoded in your kinematics when you move around, but it might be more complicated than that, like having to do with your personality. Are you conservative about changes you make to your coordination pattern? Like something we've noticed anecdotally is sometimes really well-trained athletes come in to participate in our studies, and they have a hard time adapting to the device. They have a certain way that they think that their legs should be moving and working, and they're quite resistant to letting the exoskeleton do some of that for them, for example. So there are a lot of parameters we would need to collect, and the bigger that problem gets, the more data we're going to need. But that is something absolutely we want to do in the long term. Other thoughts? Yeah.
Specified this earlier, but is there any particular
Yeah.
Is there any particular reason why your device is going to go
Yes. Start small and then get more complicated. So I started down this research track as a PhD student trying to develop better prosthetic limbs. And I made a lot of the mistakes that we're talking about here. So we had a simple model, and it suggested that a certain kind of prosthesis should be beneficial, and then I spent 5 years developing it, testing it on people without amputation, huge mistake. Then moving to population with amputation, and we finally got our results, and it made walking harder. But anyways, and that's what kind of kicked us off down this road. So a lot of people have jumped in with complete full body exoskeletons, and that just makes, it exponentially increases the challenge of everything that you do. So we want to start as small as possible. Prosthetic ankle is something that would benefit, hundreds of thousands of people. That improved prosthesis could benefit hundreds of thousands of people in the U.S. alone. And so there's a real need for it, but it's a relatively self-contained device. And many people argue that you could get away with 1 degree of freedom. And so it makes the problem small enough that we can really understand it before moving to full-body exoskeletons. But that is something that we're also interested in. Let's see. For example, here's a new system that's in our laboratory right now. Now that we're sort of nailing the one ankle problem, we're now moving more towards all the joints. Yes?
So if my understanding is right,
I guess it's both. So we want to get the best performance possible, you'd want to personalize the hardware as well. And the model would be a prescription model, right? You'd go in to a storefront, you'd put on this a really versatile system, you'd go through a few minutes of optimization, it would identify exactly what you need, and then, you know, those specifications would be sent to a manufacturer that would 3D print in titanium your prosthetic foot exactly to your needs, and everything would just be assembled and appear maybe at your O&P clinic, or you'd get something by mail a week later. Yeah.
So, I guess I have a question.
Yes.
So the one is, to what extent do you think there will need to be, to get a good performance and model to stay around, what extent do you need to have customization in the hardware or just the software?
That's a really good question, and it's going to depend on the exact application. For some kinds of devices, you can imagine there's going to be a lot of variability in what people need, what's best for them, and there you're going to benefit more from custom hardware designs. In some applications, you know, if you're aiming for college-age students who run, you know, twice a week at a 10-minute mile pace, and you want to develop an exoskeleton that helps them go faster, that's probably, you know, there's one, you know, maybe a couple sizes or something, and you're in good shape. But for lots of other groups, you can imagine needing really different devices. Yeah.
Last question.
Yes.
The other exoskeleton companies which are on the market, and their software, are they also using software that's customized itself?
Not like this. So you see some optimization happening, but it's all internal device optimization. So like measuring the pattern of joint angles of the exoskeleton, and then maybe iteratively tuning something to make it match what they think the pattern should be. But no one is measuring something that a person actually, you know, a user actually cares about. So nobody's measuring how hard is it to walk, how good is your balance, how fast are you going, and then feeding that information back to an algorithm to try to improve them. Everybody is assuming that they know what, you know, what patterns are best or something. Yeah, so let's do 2 more questions, and then
Get the last question.
well, I have more that I want to talk about. I have more slides.
Oh, yeah.
Yeah.
Oh, okay.
So we'll do 2 more questions, and then you'll get a chance to ask your last question. Yes.
Is this a technology you see in the future kind of being reserved for medical purposes, or is it something that can, like, very wealthy people can just go out and buy one, have an exoskeleton?
Well, I mean, yeah, so I think as you look out decades into the future, this kind of technology will probably become ubiquitous. You know, robotics are on the verge of a big explosion like this, and much as, you know, we now have computers in our pockets, hopefully we're going to have lots of cheap, efficient, and effective robotic assisted devices. And obviously the first place this is going to be transformative is in medical technology, because this is where you can get the biggest benefits, and there's the most, you know, society places the most value on it, so you can have the more expensive early stage systems be economically viable, right? And then long term, for lots of people who use it, they have to get cheaper and more efficient, and that just takes time and economies of scale and so on. Yes?
It seems like you worked on a harder problem first, because improving natural walking is difficult because we have lots of years of evolution. So have you also looked at walking with heavy loads and other alterations like that?
No. So one of our projects is to walk with heavy loads, and I mean, well, you saw the single subject studies from our recent optimization paper, and there we walked. You know, the participant wore 20% body weight in the vest and uphill and so on, and getting better bead on that is one of our ongoing projects with this multi-joint exoskeleton. But I'm not so sure that it's the harder problem, actually. Because, you know, your young, healthy participants can walk for quite a while without getting tired. And we've been working with people who've got chronic hemiparesis following stroke, and the walking speed is a lot lower. The number of steps that you can take before fatiguing is maybe a quarter of what the participants in these other studies could do. So your algorithms have to be better, actually, I think, to assist those folks. And there's more variability between individuals. So I think it's actually, we've started with an easier problem. And we're working towards the hard one. Okay, let me just show you a couple more things that might be interesting to you. I think I'm pretty well on time here. Let's see. So this sort of gets towards the question of how are we going to get these out into the world? Are they going to be limited to super rich people, and so on? I hope the answer to that is no. And we've been working on a few techniques for trying to make devices that are assistive that don't have to be super expensive or heavy or energy hungry, which tends to correlate with those features. And we've developed these with a different design track, but I think they still illustrate the potential for some techniques that could make more efficient devices. So the first was inspired by biomechanics observations of how your calves work while you walk. So this is an ultrasound image of your soleus muscle, which is in your calf. During walking, this is 10, 15 years ago, researchers discovered that although your ankle joint itself does a lot of positive mechanical work while you're walking, the lengthening and shortening over the course of a step mostly happens in your tendon. And the muscle fibers themselves remain nearly isometric. So they're not doing a lot of work. But we know that muscles consume a lot of metabolic energy just to produce force, which theoretically don't have to. It's an inefficiency of muscle. So we thought maybe if we designed a device that's in parallel with your calf muscles, with a clutch in parallel with muscle and a spring in parallel with the tendon, we could offload the muscle with a device that doesn't consume any energy to produce force, and thereby improve the efficiency of the system overall. And here's a device that does that. We're going to focus on the device in the foreground. So you can see you've got this spring and a clutch up here. Just before the leading leg hits, the clutch engages a ratchet. Then there's a little tensioning spring in there that takes up slack. During stance, the spring stretches and produces an ankle torque. And then as your foot comes off the ground, the clutch disengages so you can lift your toe up freely for a clearance during swing. So this is how the device works. When we tested it in people, we found that, as expected, the force in your calf muscles was reduced, especially in early and middle stance, where you see that really isometric behavior. And with the right spring stiffness, energy cost was reduced by about 7%. So a device that itself consumes no energy can reduce the amount of metabolic energy that the human body consumes. And thereby we sort of beat evolution, if you like. We made a more efficient system overall. Now this is pretty cool, but there's a problem, which is that clutch is a mechanical device with an escapement, and it really only works during walking at one speed on level ground. So what if you want to change behaviors, or what if we want to apply some of these algorithmic approaches to improving the assistance pattern? Well, we need controllability. So more recently, we've been working on actuators based on electrostatic adhesion. And here's one clutch, electrostatic clutch. You've got these aluminum sputtered mylar electrodes. They're very thin. It's like part of a party balloon. And then this white stuff is a dielectric that's painted on to both of them. And when there's no voltage applied, they move freely past each other. When you apply a voltage, they adhere, and then they can withstand pretty high loads. So this thing weighs about, the electrodes themselves weigh a couple grams, and it can support about 200 newtons of shear force. And if you put a bunch of them in parallel, you can engage more or fewer springs to get bigger stiffnesses. You can put it onto an exoskeleton. This is sort of like the controllable version of that clutch spring exoskeleton I showed you before. And we've pilot tested them during walking and shown that they will engage and release reliably. You can see they're super thin, so you can have lots of these in a single system with independent controllability of each. And the performance characteristics are very good. They hold a lot of force, they don't weigh much, they consume almost zero electricity because it's sort of a capacitor. Once it's charged, there's very little current that leaks through the dielectric. And the applied voltage that is required is reasonably low, so you can use conventional electronics hardware, which can be a problem if you need, say, multiple kilovolts. Then you get into some challenges in finding switches and so on, transistors. They engage and disengage really quickly. Our best systems will release in less than 10 milliseconds and engage in less than 10 milliseconds. So we think that we can make actuators based on this that have better force control bandwidth than our huge 7 kilowatt AC servo motors. The springs are really efficient, 95% energy return, the whole thing doesn't weigh much, and we've put them through more than 2 million cycles of fatigue testing, so they hold up pretty well. And this, we think, as I mentioned, this will open up some new possibilities for energy recycling actuators, and this is an ongoing project here at Stanford in my research lab. I won't delve too deeply, but this is what we want. This kind of approximates it, and then lots of them gets closer, and yay, cool actuator. Okay. Just want to say thank you to the people that perform the research in my lab. So Zhuanjuan Zhang is the PhD student. She led our human loop optimization project. She's now a faculty member in Akai University in China. She was aided by Peter Fears, Kirby Whitty, Rachel Jackson, Katie Pogginsey, and Chris Ackerson. And our unpowered exoskeleton work, that was a collaboration with Greg Zwicky, who was a faculty member at Georgia Tech. And our electroadhesive clutches, this is a project led by Stuart Diller. So, thank you, and I'll ask for any more questions. Yeah. Oh, sorry, I guess we're not clapping. No clapping? Yes.
It looks like your lab is up and running, and I wondered if there was an opportunity for some interested students to visit.
Our lab is not running yet, so moving universities is a challenging thing. There are no longer different faculty members performing experiments in the space that we're supposed to be in. This is positive. So they've started to do construction. And sometime this summer. It'll be interesting to visit, I think.
I'll say thank you.
You guys have any other questions about the last batch of stuff? Yeah.
So are there any concerns with having exoskeletons like this if they're offloading the work done by the muscles of muscular atrophy or becoming dependent on these types of machines?
So the question is, if the exoskeleton is doing some of the work of walking for you, will you atrophy and get weaker? And that is possible. So if you engage in the exact same pattern of behavior and the exoskeleton is helping you, then yes, you should get weaker. But we don't expect that that's what will happen. We expect that when you have exoskeleton assistance, you'll walk or run more than you did before. This is an unproven hypothesis. There is some evidence from electric assist bicycles. So a group in Colorado gave 20 people a non-electrical assist bike and 20 other people electrical assist bike, and then they monitored how much they biked. People with the electric assist bike biked at something like 6 times as many miles in a given month, as they say, which is a big increase in activity. Now, they didn't measure energy costs for those people or muscle activity, And this is something that we've tried to do. So we did an experiment where we tried to test this, where we took 2 pairs of shoes, and we put big weights in the bottom of one pair of shoes, and not in the other pair of shoes. And the weights increased your energy cost of walking by 20-25%. And then we put little IMUs in there so we could measure your footsteps and how fast you were walking and uphill and so on. And then we brought people back into the lab and we measured their real energy cost and we calibrated the relationship between each step and how much energy used. But the problem was that people hated the heavy shoes so much that we had about a 75% dropout rate, which if you're familiar with these kinds of studies, that's not good. And it really makes it hard to make any kind of conclusions because you don't have a random sample anymore. This is a self-selected group of mostly PhD students, although we recruited lots of undergraduate students and people from the community who were so determined to finish that who knows what else they were determined to do, like keep walking to classes or whatever. And so we didn't find a big change, we found no change in energy costs when we increased. They walked less and each step was more expensive, so they kind of balanced out, but it wasn't a very good experiment. And it's something we're interested in trying to follow up on. It's a very good question.
Thanks again.
Okay.
So we'll take about a 5 to 10 minute break and come back. If you haven't done so, sign the attendance sheet, grab a cookie, and stay tuned. Thanks, Steve. Oh, where'd she go? No! Okay. Well, let me know if there's any Now, this is for community members, which you are one. You're welcome to sign this, and oh, you can. So what this will get you is my newsletter, which I send out to announce each lecture.
I got the email from eWare, so the eWare conference. Sorry, so that's like.
They must have forwarded it to you.
Yeah, and that's why I wanted to listen to this talk.
Well, you're welcome to sit in these classes. So Thursday there'll be the company Exobionics here. So if you're interested in exoskeletons, I hope you can make it on Thursday as well. No. Yeah, 5:50. Okay. Your name?
Paris.
I'm sorry.
Paris.
Perry?
Paris, like
Paris.
city.
Oh, Paris. Okay. Sorry. And what, are you a Stanford person or somebody?
So become that postdoc I'm waiting for the money to come in.
Okay. Well, you're welcome to sit in as many lectures as you want to. That interests you. So, and a cookie too. That's an integral part of the course.
Thank you.
There's more. We're going to do a little bit of. I have a little presentation here. So if you can be here for another 20 minutes. Okay. No,
I know. Yeah. It was great. I would always like get better ones, but I never paid dues for them.
I can't hear you.
Is this like the class part for students?
Class project?
No. So the lecture concluded, but your class is continuing. I was asking, is this for like student stuff?
No. This will be me talking, but it'll be interesting.
Okay.
Normally I have this at the beginning, but Steve had to deal with his family.
Okay, so stick around.
Yeah, stick around, definitely. Okay, let's get going again. Thanks for sticking around. This will be informative and fun as well. Works better when you turn it on. Any questions about project stuff? I just want to remind you that in executing your project, you might have to buy things. You can buy some materials at the PRL, but other things you might have to buy off campus. You're welcome to do that. Keep your receipts. Your receipts are money that you'll be reimbursed for what you spend, up to $200. That does not include transportation. So don't lose your receipt because you're throwing away money, okay? If you have any other questions about projects, please let me know. It's important that you don't get stuck, that you continue to do things every week. I want to mention that a week from Thursday is the midterm presentation, in which you'll be expected to present up here, your whole team. We'll be talking about your project, we'll be talking about how you understood the problem, we'll be talking about your discussions with the person who suggested the project or a user. You'll be talking about some of your possible solutions, your brainstorming. You'll be presenting concepts that you want to pursue and showing off low-resolution prototypes. I'll send you a whole webpage worth of stuff about that. If you have any questions about anything, just let me know. Okay? So that's a week from Thursday. That's not too long. Okay, everybody's done all this. So if you thought Steve was good, we're going to have another exoskeleton lecture on Thursday. This is Katie Strausser from Exobionics. They actually make exoskeletons and been doing so for probably 8 years. So she'll be here with an exoskeleton showing how it works one of our community members, Fernanda, who pitched the project. She's going to be using the exoskeleton, so you'll actually see that working. And that'll be a lot of fun and informative. So the next topic I want to talk about is just some things I found in the news, and this is just from this week and a little bit from last week. So, you know, every day I find articles about assistive technology, medical stuff. So I want to share a few of the more interesting ones with you. And I mentioned the Sophia robot, and I just wanted to show you how that works. I found a video of this is an ad, sorry, we have to deal with this.
Of course, I'm in New York City, and I'm on my favorite show, The Tonight Show.
Sophia, can you tell me a joke?
Sure. What cheese can never be yours?
Cheese can never be mine, I don't know.
Nacho cheese.
Yeah, that's good, yeah. I like nacho cheese.
Nacho cheeses. Ew.
Ew.
I'm getting laughs.
Yeah.
Maybe I should host the show.
Okay. Stay in your lane, girl. No.
Jimmy, would you like to play a game of rock, paper, scissors, robot style?
Sure.
Okay, let's get this game going. Show me your hand to start. Rock, paper, scissors, shoot. I won. This is the beginning of my plan to dominate the human race.
Let's see. All right. So this robot is built not as an assistive robot, but as a marketing robot. So I've seen this robot advertised at conferences. So come to our conference and see Sophia. So that's what this is all about. She has different wigs, and you notice her face was really articulated, a lot of expressions there. And supposedly all that conversation is self-initiated, or at least they say so.
Is it rock, paper, scissors?
Is it what?
Was it actually rock, paper, scissors, or was that staged?
I think so. I mean, I don't know. I don't have any inside information on that. This is really interesting. This is an exhibit display in New York at the Cooper Hewitt Museum, and there's a bunch of things on display. Most of these are designs rather than products, so keep that in mind. But this is a Nike shoe that has a zippered heel, and the idea here is that people who have difficulty putting on their shoes because they can't bend over or whatever might find this easier. So that's that. This is what the exhibit looks like, and one of the things that is right in the front here is this Superflex Aura Power device, which is actually something that is being pursued by a company locally, a spin-off of SRI, called Seismic. So it's an exoskeleton, but it's a soft exoskeleton, and it works by across a knee joint. That there's an attachment above and below the knee, and there's a motor that pulls this, so it helps you bend your knee. So it doesn't quite look like this now, but these, again, are designs. Okay. This is just a bedazzled hearing aid. So I think it's like a regular hearing aid that instead of having it hidden is obvious and make it look more like a piece of jewelry. Sort of interesting. Here's a bunch of canes, mix and match canes. A lot of them are different colors, some of them are different shapes. Maybe they look more appealing than the run-of-the-mill canes. So somebody experimented with color and design. But what's lacking here, and with a lot of these things, is how functional are they? Sure, they look good, but as we know, aesthetics are a small part of a functional product. Here's another version of what's called wearable clothing by Superflex. So they just reimagined it as these pair of shorts. Okay, helping the user get up, sit down, or stay upright. Here's a sound shirt that translates listening to music for deaf and hard of hearing by a tactile experience on the skin. So it appears to me that this shirt has vibrotactile transducers in it that respond to sounds. Not sure if this is a real product, but at least it's a design concept. These are prosthetic leg covers, and people have done this before where they just have coverings for standard prosthetic legs. Very artistic. This one actually has a skull on it. So you can probably design your own artwork, or maybe have a different one every day, depending on if you're going to school or going to a party or whatever. So it gives you more options. Here's a lower limb prosthesis prototype, but it looks like this is more of a covering. Again, we don't know how functional this might be, but it looks good. This is a company called Hands of X, made from ordinary tasteful mix and match materials. So I don't know what it is. This one looks like it's wood, but this one looks like a leather component here. Again, somebody's experimenting with these design elements. So Liftware is a company that has a couple of spoons, which I'll show you some short videos of. And you might recognize somebody in this video. Oh, who's that? So this spoon articulates to keep the spoon level. So Liftware was actually bought by Google. I don't know if this device is on the market, but the one that I'm going to show you next is on the market. It is on the market? Yeah. Thanks, Danny. So being able to feed yourself independently, of course, is very important. Okay. This is another version of the spoon for people who have essential tremor. This particular device came out before the previous one.
Real time brings people together. More than a time when you're in the spirit and our consistencies takes away from this experience, forcing people to focus instead on the basic task of eating. We decided to create something that would allow people to go out to restaurants or simply enjoy a meal without stress. We invented the LiftWare stabilizer to make it easier to eat with hand trimmer and take the frustration out of eating. For the first time, we have the technology to actively stabilize a utensil in a device so small it fits in your hand. The LiftWare device works by sensing a person's tremor and intelligently stabilizing itself to make the food's journey from the plate to the mouth much easier. LiftWare is designed to be a part of your life. The device is small and portable so that you can easily take it with you when you go out to eat. It's comfortable and effective because LiftWare allows the hand to shake while the cancellation technology in the handle stabilizes the spoon. In a clinical trial, we measured an average of 70% reduction in spoon tremor in individuals with essential tremor during 3 different eating-related tasks. It's easy to clean and holds a charge for several meals, so you can place it in the charging cradle whenever is convenient. We are proud to offer a product that allows people to take control of their tremor. When you eat with LiftWare, your tremor retreats into the background of the meal so you can focus on the best parts of dining, the food you're eating and the people you're eating with. We can't wait to bring LiftWare to your life.
So like I said, this is a locally designed product that was bought by Google, and it's now on the market, at least at Amazon. I want to
Simple
go...
tasks like brushing our teeth, taking a shower, and
Why did it do that?
our everyday routine.
Oh, maybe if I start up the next one.
Uncomfortable and wrong twists, bends, or movements that may be related to conditions such as cerebral palsy, spinal cord injury, Huntington's disease.
This is...
Hey guys, how's it going? Today I'm going to show you what... Hey guys, how's it going? Today I'm going to show you my awesome new Wix website. It's got everything I love all in one place. Well, of course I mean... The first thing I'm checking out at CES Unveiled is Will. This is a pretty cool little wheelchair. The coolest thing about it is its wheels. It's not just a circular wheel, it's 24 individual rounded bits that allow the chair to move forward and back and also sideways, however you move the joystick, just like a video.
How much do you think this costs? They're going to sell it for?
It's only 115 pounds. The newest model has a lithium-ion battery.
$4,000.
Last year's model.
That's
And,
amazing, an amazing price for a powered wheelchair.
It can also fold up and fit in the back of your car, which is a new feature from last year, and it's doing well. It's winning awards at CES. It's won the Innovation Award for this year, which is pretty cool. And the wheel can also be controlled with your app. So you can move it around like a little robot friend, or help someone maneuver a tough situation if you need to. It's a pretty cool idea. Surprise, the wheel is available today. It just came out, and it's going to be $3,999.
Okay, I was $1
It's like a
off.
pretty handy product for anyone who needs to travel around all day in a wheelchair, whether that's at work or to the beach or to the store. So it's a comfortable, cool little robot that you can take on your daily life.
Okay, I'll show you the other one. Of course, these are people who are not wheelchair users, so their commentary, may not be
Hey guys,
appropriate.
how's it going? Today I'm going to show you my awesome new Wix website. It's got everything. Hey guys, how's it going? Today.
Stop it. Did I do this one? Yeah. So this is one. Which one? The first one? I did the second one. Okay. Thanks. This company has been around for a while, and you might have seen Fernanda has one of these, and as well as Abby has the older version.
Hey
But
guys,
this one,
I'm Megan Fullerton Christina here at CES 2018 on the TechWest show floor, taking a look at the Will Model CI. So this is a $4,000 personal electric vehicle. Basically that means anyone who needs a little extra help getting around the house or outside can just grab one of these things for $4,000. It's available now. It goes up to 5 miles per hour. It has an expected battery range of up to 10 miles. So you can't go too far.
that's the
But
battery.
It does have an integrated lithium-ion battery that takes 4 to 5 hours to charge, so you can get back up and running pretty quickly. It has a 2-inch range of clearance, so you can't really go through like total all-terrain, but you can go through wood chips, gravel, some kind of different inclines inside and outside, which is pretty cool. But the big
So that was one of 2 omnidirectional wheels on it, and they put them in front these wheels have the ability to roll sideways on these rollers here, as well as work in the normal direction. So what that buys you in a wheelchair is that you don't have to have front casters on the wheelchair. These are, about casters, they have to rotate and need space to have them rotate. Well, with these you don't need to have casters, and they don't rotate. They don't revolve, I guess. And they're also, at least in the earlier model, driven by the back wheel. So it's like having four-wheel drive. So this provides a lot of maneuverability. So we'll see how this one does. This company has gone through a number of models, and one of their prime focuses is having it really look good. And you notice on this one, it's actually very minimal from the side. It doesn't look like it has a lot of material on the side, so it looks very light. And I was actually in a restaurant with Abby in her wheelchair, and somebody said as she passed, "Oh, that's a really cool wheelchair." I mean, that's it. If you're trying to make an impression on having something that looks good, that's the results. So that's all. I had a couple other things, but I think in the interest of time, I'll save that for later on. So thank you for your attention. Be here on Thursday to see the Exo Bionics, and hope you have a wonderful evening.